1. How quantum networks could unlock the secrets of quantum gravity. 2. Exploring the quantum internet. Insights into spacetime curvature. 3. Quantum gravity breakthrough. How scientists are making spacetime tremble physics revolution. 1. How quantum networks could unlock the secrets of quantum gravity. Here's a mind-bending truth. Despite quantum theory's undeniable success, it's still incomplete. Gravity remains the stubborn force that refuses to fit into its framework, leaving physicists chasing the dream of a unified theory of everything. But a groundbreaking idea from researchers at the Stevens Institute of Technology might just change the game. They propose using quantum networks, yes, the same technology poised to revolutionize communication, to finally probe the elusive link between quantum mechanics and gravity. And this is the part most people miss. It's not just about theory. It's about building something tangible to test these ideas in the real world. Let's back up for a moment. Quantum mechanics elegantly explains 3 of the 4 fundamental forces: electromagnetism, the strong nuclear force, and the weak nuclear force. Gravity, however, has always been the odd one out. Einstein's theory of relativity tells us that gravity isn't a force in the traditional sense but a curvature of spacetime caused by mass. Think of it like this: the Earth appears spherical from space but flat from the ground, a concept known as a manifold. Einstein extended this idea to spacetime itself, where mass warps 3D space through the 4th dimension of time, creating a 4D curvature. This is why we don't live in a straightforward Euclidean 3D world, but in a dynamic, curving 4D spacetime. The problem? Our brains aren't wired to perceive this reality directly. Relativity makes precise predictions about how mass curves spacetime, most famously observed through time dilation. For instance, time slows down near massive objects or at high speeds, a phenomenon crucial for GPS technology. Without accounting for time dilation, your phone's GPS wouldn't work. But here's where it gets controversial. Quantum mechanics has no room for gravity or its effects on time. This disconnect has fueled decades of debate and theories like string theory, causal set theory, and more. Yet, none of these can be tested directly until now. The Stevens Institute team suggests using quantum networks of entangled atomic clocks to measure time dilation caused by gravity. These clocks, kept in quantum superposition, would theoretically stay perfectly synchronized according to quantum mechanics. But relativity predicts they'd fall out of sync due to gravitational differences. By placing these clocks at varying altitudes, say, one at sea level and another on a mountaintop, researchers could observe whether they remain synchronized or diverge. This experiment wouldn't just bridge quantum mechanics and relativity. It could reveal entirely new physics. But here's the kicker. What if neither theory fully explains the results? What if the clocks behave in a way that defies both quantum mechanics and relativity? This experiment could open the door to a grand unified theory, reshaping our understanding of the universe. And while the technology for such quantum networks is still in its infancy, the potential is undeniable. So, here's a question for you. Do you think this approach could finally reconcile quantum mechanics and gravity? Or will it uncover something even more profound? Let's debate in the comments. The future of physics might just depend on it. 2. Exploring the quantum internet. Insights into spacetime curvature. What if the 2 foundational pillars of modern physics are locked in a silent, century-long conflict? On one side, we have Einstein's general theory of relativity, a masterpiece that elegantly describes the grand cosmic dance of planets, stars, and galaxies through the curvature of spacetime. On the other, we have quantum mechanics, the stunningly accurate, if bizarre, set of rules governing the microscopic realm of atoms and particles. For decades, the inability to reconcile these 2 theories has been the most profound challenge in physics. But now, a team of physicists believes they found a way to eavesdrop on this conflict using a technology straight out of science fiction: the quantum internet. While most of us are familiar with the internet powered by electrons in wires or light in fiber optic cables, researchers are hard at work developing its quantum successor. This next-generation network isn't just a faster version of what we have. It's a complete paradigm shift. Instead of classical bits of information, a quantum internet would transmit data using the strange properties of quantum mechanics itself. Imagine particles that are intrinsically linked or entangled, so that measuring one instantly influences the other, no matter how far apart they are. This capability promises to revolutionize data transmission, making it exponentially more powerful, efficient, and unbreakably secure. This technology is still in its infancy, a long way from streaming movies to your living room. And this is the part most people miss. Its first groundbreaking application might not be in communication but in cosmology. New research, detailed in the journal PRX Quantum, outlines a pioneering experiment that could use the building blocks of a quantum network to explore how the fabric of spacetime, as described by Einstein, directly influences the quantum world. This would be the first experiment of its kind, moving a long-standing theoretical debate into the realm of tangible physical testing. As lead author Igor Pekovsky, a professor at the Stevens Institute of Technology, explains, the interplay between quantum theory and gravity is one of the most challenging problems in physics today, but also fascinating. Quantum networks will help us test this interplay for the first time in actual experiments. So how would it work? The team proposes using incredibly precise atomic clocks, but with a quantum twist. They plan to link 3 quantum bits, or qubits, together in a special configuration known as a W-state. We already know from Einstein's work T3. Quantum gravity breakthrough, how scientists are making spacetime tremble physics revolution. Imagine a world where gravity as we know it is turned on its head, where the very fabric of spacetime quivers under the influence of quantum waves. For over 100 years, scientists have grappled with a fundamental contradiction in modern physics. On one hand, quantum mechanics rules the microscopic realm with its principles of uncertainty and superposition. On the other, gravity has stubbornly remained a force explained by classical physics. The quest to merge these two frameworks into what is often referred to as quantum gravity has been one of the most ambitious goals in science. This is not just a theoretical pursuit. Without evidence that gravity behaves in a quantum manner, our technological advancements and understanding of the universe's origins are significantly limited. The influence of gravity on the universe is profound. Phenomena like black holes, the Big Bang, and even the nature of spacetime itself remain partially elusive as long as gravity resists being described in quantum terms. The urgency to bridge this gap is growing, and scientists are actively seeking methods to explore the force that binds the cosmos. In a groundbreaking development, physicists have crafted an experiment that could reveal gravity's quantum characteristics, not by gazing into the depths of space, but within the confines of a laboratory at MIT. Researchers from Aalto University have introduced a novel theoretical model that attempts to describe gravity through the lens of quantum mechanics. Their approach seeks to incorporate the force into the standard model of particle physics, a pursuit that has captivated scientists for decades. Should this framework prove valid, it could illuminate some of the universe's greatest mysteries, including its very inception. This work has been documented in the journal Reports on Progress in Physics. This innovative theory has the potential to revolutionize gravitational studies. For years, physicists have endeavored to construct a unified theory that links gravitation with the other fundamental forces, electromagnetism, and the strong and weak nuclear forces. The challenge lies in reconciling two frameworks that inherently clash: quantum field theory, which describes particles and forces at minuscule scales, and Einstein's theory of gravity, which elucidates the interactions of massive objects like planets and stars. Interestingly, even everyday technologies like smartphone GPS rely on Einstein's model of gravitational force to function accurately. In their study, researchers Mikko Partanen and Jukka Tulkki detail how they employed a mathematical structure known as a gauge theory to tackle gravitation. Gauge theories already account for the other fundamental forces, such as electromagnetism, so applying similar concepts to gravity could be a step toward integrating all four forces into a single coherent framework. Rather than adhering to the traditional spacetime-based approach of general relativity, their model utilizes symmetries akin to those found in the Standard Model. This paradigm shift could help overcome one of modern physics' most significant challenges: devising a theory that describes both the tiniest particles and the largest cosmic structures using a unified approach. Current models excel within their respective domains: quantum physics for the minuscule and general relativity for the colossal. The study of gravitational forces at the quantum level is notoriously difficult. One reason is that gravity is an exceptionally weak force compared to others, making its effects challenging to measure in particle-scale experiments, which require far greater precision than typical setups can provide. However, in extreme environments such as near black holes or during the universe's initial moments after the Big Bang, both gravitational and quantum effects are crucial, necessitating a theory that accounts for both simultaneously. The researchers' method employs renormalization, a mathematical tool that addresses problematic infinities in calculations. To date, they have demonstrated that the method is effective for some basic scenarios, but they are still working to prove its consistency in more complex situations. Tulkey noted that if their renormalization approach fails at higher levels of complexity, the calculations would yield infinite results, an outcome any physical theory must avoid. While a complete proof is still underway, the researchers remain hopeful that their method will withstand scrutiny. What do you think? Could this be the breakthrough that finally unites quantum mechanics and gravity? Or are we still far from solving this cosmic puzzle?